All right, so let me get started. So last class we discussed about the finite element method and how we will use the finite element method in order to solve a general problem of continuum mechanics, and in particular of elasticity. And this is the equation that we're going to have to solve, but fortunately we have a software which is going to help us to do that. And let me check that this is still recording. Hopefully it will be, yes, okay. I should be on in just 1 sec. But basically, you know, I'm looking at the equations of the weak solution of elasticity with those integrals. Well, we're going to have a software that's going to help us solve that. And come on, what's going on? All right, well, I try to get this started. Let me ask you, did you install the software, FreeFEM++? Yes? Okay, did you run it? Not yet? All right, so go to Canvas and go to Files, and in Files, in project number 4, you will find a file that says FreeFEM tutorial. Did you find it? And it's a PDF. Oh. And that PDF, I like that you open that PDF and read through that. Okay, this is starting now. And there you will see there are some sections. You will have basically the theory of how to get that weak solution that we derived in class. And if you continue scrolling down, you will see a box with a code that you need to copy and paste into a text file in order to run it with FreeFEM.
What was the Phoenix project you mentioned last time?
Okay, yeah. Let me come back to that in a sec. I'm getting a little bit stressed here with this thing that is not working. What's going on? Oh, I think I know what's going on. Okay. Just 1 sec. All right, so then download that file and start making a text file, copying and pasting that text, and you should, all right, there we go. And okay, since I was there, let me finish there. We need to solve this equation, okay? And that equation, it's also shown over here. If you go to Files, and if you go to project number 4, well, right here, FreeFEM tutorial. Let me download this file, and let me open it. Here you'll find the same equation, and this is the equation, and this is the variational form with the sigmas and the, well, in this case, the stresses already with the part of elasticity, and that's what we're going to see right now, and the final equation. And what I want you to do is to start copying this text in the boxes into a file, a text file, and finish that file with an extension EDP. Okay? E as in Edward, D as in David, P as in Paul. It's going to be an EDP file. All right. So there is just one more thing we need to do in the theoretical part in order to get to the final equation that we're going to use, which is this one. And you see there is now there is a stress, or there is a shear modulus, and there is a Lamé coefficient, and we need to add that. So let me show you how we're going to get there. Okay, so we got up to here. We discussed about what the terms inside meant, and the last simplification that we're going to do is to apply linear elasticity, and also to reduce this problem to 2 dimensions. With this software, you can also solve problems in 3 dimensions. The issue is that the meshing becomes a little bit more complicated. So we're just going to do it in 2 dimensions now. And in order to reduce the problem to 2 dimensions, what we're going to do is we're going to take the matrix in 3 dimensions. Yes, I can do that. Thank you. Sigma 1, 3, sigma 1, 2. Here we'll have a matrix that it's going to be the C matrix. I'm not going to write it, but you know what goes in there. And I have here the strains. And I'm going to have here the shear strains. And what we're going to do is we're going to assume either a condition which is called plane strain or plane stress. For now, let's just do plane strain. Plane strain is going to mean that the state of strains is going to just change in a given plane, but not in the direction perpendicular to that plane. For example, if I had a wellbore and to that wellbore, let me do a little bit more elliptical so it looks like 3D. In this wellbore, in a 3-dimensional space, where this is 1, 2, and 3, I'm going to say that there are going to be no changes in direction 3. Why? Because I assume that this wellbore is so long in the direction 3 that any plane I take perpendicular to 3 is going to be the same. And at the end, that means that there is no strain, there is no variation in direction 3. So, I repeat, how I got to this is because I consider that this wellbore is so long that that's a predominant direction, that any plane I take in direction 3 is going to be the same. So if I take a plane here, or if I take another plane, another cut over here, those are going to be exactly the same. There is no variation in direction 3.
That's only true for vertical well, right?
It could be a horizontal well, and then there's going to be no variation in the direction of the wellbore.
I got my case is you are assuming that there's no variation.
In the axis of the wellbore. Okay? Whatever direction of the wellbore is, there's no variation in the direction of the wellbore. when we get to fractures, we'll see that we'll also apply this type of method in order to study a fracture. For a fracture, what we're going to assume is that, let me see if I can get this plot right. We're going to assume a plane state of stress along the axis of the wellbore, saying that the medium is just going to deform, in this case, in direction 1 and in direction 3, but it's not going to move. There's not going to be any displacement in direction 2. And the same if I take a plane somewhere over here or somewhere over here. In this case, this is not a true plane strain, because you see that this shape is different than this one and that one. But that's another story, okay? Let's just adopt for now the one of the wellbore, in which there is no variation in direction 3. Okay, since there is no variation in direction 3, that's going to help us a lot, because if there is no variation in direction 3, and therefore there is no displacement, or there is no variation of displacement in direction 3, which strain is going to be equal to 0? Sigma 3, 3, right? Let me just put this in a box. This is another example, okay? Here we're talking about the wellbore. Epsilon 3, 3 is going to be 0. And also, because there is no variation in direction 3, and this is the state of the plane strain, we're going to be able to have distortion or shear strains just on the plane 1, 2. So this square is going to be able to change shape, but since there is not going to be a change in direction 3, also the shear strains epsilon 1, 3, which is the shear strain in the plane 1, 3, and the shear strain in the plane 2, 3 are also going to be equal to 0. So this one is going to be equal to 0. These two are going to be equal to 0. And because of that, the problem is just going to be reduced to 3 variables, 3 stresses and 3 strains. And if I do that, now this matrix, now I'm just going to simplify to this one, to that one, and to this one. It's going to be sigma 1, 1, sigma 2, 2, just one shear stress to solve because the others are 0. And here the matrix is going to be lambda plus 2 times the shear modulus. I think this is the first time I use this notation. I'm going to explain it just in a sec. It's exactly the same that we have seen before. It's just a more compact version of the stiffness version, of the stiffness matrix. And here this is the shear modulus. But it's exactly the same, okay? That what we have seen before. Where this is written in terms of the Lamé coefficients, just a shorter way to write the stiffness matrix, where lambda is Poisson ratio times shear modulus 1 plus Poisson ratio 1 minus 2 times the Poisson ratio, and the second Lamé coefficient is mu, is just the shear modulus. Oh, I'm missing something. I'm missing number 2 over here. All right, this is exactly the same thing.
Can you go back to our last
Question. In a plane strain model like this one, we already said that, look at this. The strains, these ones are equal to 0, okay? And this one is also equal to 0. Will sigma 33 be equal to 0? So imagine that we have a plane like that one, and let's give it some thickness in the third dimension. You apply stresses sigma 11, sigma 22, and you do not let it deform in direction 3, but you add those stresses. Will sigma 33 be equal to 0? You say no, David? Why not? What phenomenon is causing that stress to be different than 0? What is the property of the materials that when you add stress in one direction tend to deform in the perpendicular one? It's the Poisson effect, right? So although epsilon 33 is equal to 0, sigma 33 will not be equal to 0. And sigma 33 will be proportional to the Poisson ratio and to the summation of the two stresses in perpendicular direction. So although we have reduced our problem to 2 dimensions just by solving sigma 11, sigma 22, and sigma 12, remember that still this is in 3 dimensions. It's just that we are simplifying the problem so there is no variation in direction 3. But we can still compute what is the stress in the third direction, sigma 33. This is what is called a plane strain model, because there is no strain in direction 3, but the stress in direction 3 is different than 0. The opposite of that would be what is called a plane stress model, in which let's draw again a plate or a section of some particular solid. This is 1, 2, and 3. Let's say that also we have an orifice in the middle. It's going to be plane stress when the stress in direction 3 in this case, that one is going to be equal to 0, and therefore there might be some strain in direction 3. So now we don't put any stress on direction 3, but if we add stresses in direction 1 or in direction 2, this plane is going to be able to deform in direction 3. So you can solve it with this matrix, but you have to remember that the strain is not going to be equal to 0, but the stress will be equal to 0. Okay, so in order to solve the problem that we're going to solve right now, we need to assume this 2-dimensional state of stress, because we're not going to do it in 2D. All right, so you're ready with your computers? You have the software installed?
How far do we need to copy down?
Everything. You need to copy everything, because other one is not going to run. Okay, so let me come back over here. Again, all of these, everything in the box, just copy it. All the way down, all the boxes.
For both situations?
No. Just for the first one. So let's see. Up to here, up to 3. Up to 3. And I'm going to explain now step by step what all of those are. All right? But in order to do that, I'm going also to open it on my computer. And before I open it in my computer, I wanted to point out that in case that you couldn't install the software because it's your work computer and you don't have administrator rights, you can also run it online. So you go to this address and then you click on try it online. You just copy the code in here and this is what you're going to get. All right? So let's actually try it first online. And then we'll go to the actual software. Because there are some things that you're not going to be able to do online, so you have to install it at some time.
So after we copy everything, should we just save it and then open it without opening?
Well, if you just go where in the online version or
No. So I just wrote it.
yeah, and then just save it as EDP and that's it. And just save it in a known folder. And then what you have to do is you can run it, guys, online or directly in the actual software. Once you save the file, what you're going to have to do is, for example, let me see. I have it here. This is the software this is the script I'm going to run, Kirsch Shopkun, and I have it in this address. So what you have to do is you go to open a terminal or a command prompt in Windows, or if you are in Mac, I think it's just called terminal. You go to that particular location with CD, and then you paste the address. I'm already there, right? But okay, let me get back. So if I were to be in my root folder, it will be something like this. And then you put CD, which stands for create directory. You paste the address, press enter, and you get to that directory. You guys never play with DOS, right? I did when I was teenager. I started with DOS. What?
I just opened it with the app before. If this is where
Yeah, okay.
I saved it here, how do I? You had up on top of the listing.
Okay, so go here. No, go to properties.
Oh,
In,
on which?
in that file,
Here?
here, go to properties. And should be
Get info?
get info, yes. And there you have the address. This is the address, all of that.
Okay, so where?
Yeah, that. And then just copy that. And then go to the terminal and type CD.
Type CD.
Yeah, space. Open quotation marks, just one. No,
With
that one. And okay. No. No, delete. Delete.
delete the last one?
Yeah, delete what says open now. Okay, now paste your address and close the quotation mark. Enter. Didn't work? I'm not sure that it did it.
Okay, because before I've just gone to the FreeFEM and it makes you choose a.
All right, guys. Also, if you install the software, you just can do double click in the EDP file. I think it's going to work too. Okay? Can you try doing just double click on the EDP
I
file?
just clicked.
And then find the FreeFEM link. Okay? And did it run or not?
Because you can even open it and choose a file, and the trial one works when I open that.
Oh, probably if it didn't work, it's because there's a mistake. Okay, open the trial one, and let's see what happens. But okay, I think you guys are going to have all sorts of problems now, but I'll help you one by one. But just let me, before we get there, let me explain what goes on here in the code. Okay, so so in order to make sure that there is no mistake in there. Okay, so the first thing that you have to do in this code is to, in order to make a comment, you do the double backslash, and whatever you put after, that's a comment, all right? So here, I just added a line just to separate the sections, what goes in there. In order to define a real variable, you write real, the name of the variable, equal to something. And you need to finish every single line with a semicolon. Like, for example, here, I have a variable which is called y size equal to 1. And then I do add a comment saying this is the domain size in direction y. Sometimes this code, it doesn't take a float number unless you put a decimal point there. So make sure that, although sometimes may be redundant, just put the decimal point in there. So I have these 3 dimensions, 3 variables. I have my elastic constants also defined the same way. Here, I'm already doing mathematical operations based on the previous variable Young modulus and Poisson ratio. I just create a new variable, g and lambda. These are the 2 ones that we just saw in our equations that we need, which are mu and lambda, or g and lambda is the same. Next, I have values that are going to be my boundary conditions later on. All right? So far, it's just definition of variables. Again, every single variable should finish with a semicolon. Okay, second part. We have the boundaries. Here, the software is going to need a closed boundary or a closed domain. This was our potato. Your potato cannot be open at some point. It has to be closed. It has to be a closed domain. And the way that FreeFEM is going to do this is going to take an input, is going to create an input. Anything that you do clockwise, here I'm defining 4 lines. If you close that clockwise, it's going to create a surface. In order to add the wellbore, what you have to do is to create a domain counterclockwise. And when you do that, first of all, you will create a surface, but after you add that new line, it will subtract that. So we'll create a hole. And this is what you see over here. This starts with the right boundary, so it starts with this one. Then it goes to the top, it goes to the left, goes to bottom, and that's the end of that loop. And for the well is the other one, and you see it's an equation of a circle.
Is the order you type those in important?
The order that you type this, it's how it goes. So it goes right, top, left, bottom, and then it goes like this.
Yeah.
Yes.
I'm just noticing copying the code from the page.
It introduces some errors.
Adds spaces in between.
Oh,
almost
okay,
every
okay.
single- yeah.
Oh, okay. That's going to be then a huge pain for you guys. So let me see if I can do something now about that.
Yeah, almost every single word.
So okay.
But looking at your code up there, it's easier to
Mm, okay, okay. I can solve that. Okay, I'm going to give you the code, guys. So you can download it now, okay? So you can download this one, Kirsch, download it, and you can, right. But you're going to have to modify this code so that you do the solution for the hydraulic fracture, okay? So you need to know what goes on in here. Again, okay, we were at the boundaries. Boundaries, then counterclockwise loop, it will create a surface. Clockwise loop, it will subtract it. And let me actually now run it from my computer because I want to show what this is going to do. Okay, here I'm running the code. It should look something like this. So this is the first thing that you see. These are all the boundaries. So 1, 2, 3, 4. Those are those two borders that we defined. And there is another one here that starts here and goes counterclockwise up to there. You can do zoom in and zoom out with the plus and minus buttons in your keyboard. That's what I'm pressing right now. This is the first step. Define your boundaries with lines and make sure that they make a closed loop. All right? So we are right here. Show domain. The next step, now that you have a domain, is you have to create a mesh. So this is a numerical solution, and a numerical solution needs to discretize all the domain in several points in order to approximate the solution with linear interpolations between those points. That's why we need a mesh. And that mesh, as you can see over here, is going to be made up of triangles. By default, the software is going to choose triangles. And what this is going to do is I'm going to create a mesh with this command, and this mesh is going to be composed by, these are just some integer variables. Is going to build a mesh with, when n is equal to 10, with 10 elements on the right boundary, which was this one, 10 on the top, 10 on the bottom, and I forgot the left one, 10 also on the bottom, and look, 40 at the wellbore. Why we want 40 at the wellbore? Because if we just have 10, this will be 2 cores. Let me change it by 10. Yes, it has different numbers because I wanted to make it a little bit more precise.
Okay.
So if you want to change the numbers now, just feel free to change them as I'm changing it here. And you should get the same thing. So I'm going to make it run again. And you will see how it looks with 10. 10 is not going to look good. You see, that solution now has very few elements around that circular boundary, and it looks ugly. We do not see very well what is the stress around. So in order to have more refinement around the wellbore, I'm going to put more elements around the wellbore, and let's say now I'm going to change it to 50. Make it run again, and it should refine it in this region because I'm telling divide this circle with 50 linear segments. And now I have 50. And you can see here I should have 10 triangles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 segments. you should be careful when you make your mesh that the triangles look like triangles, like with the sides are more or less the same length. Otherwise, if one of your sides is too small, that's going to lead to some numerical errors, okay? So make sure your mesh looks nice, and I'm going to press enter now in this domain, and this is what you get. Again, I press a plus sign, and as I get close to the wellbore, it looks like very nice mesh with almost equilateral triangles. Yes. So if let's say that I change one of these to, I don't know, I'm going to change the right boundary to 2 elements. You'll see this is going to look very ugly. So plus minus sign, you should be able to zoom in. Yeah. Probably you need shift.
Oh, but it's all about where my mouse is pointing.
Yeah. Yeah, it's going to zoom in or zoom out centered on the mouse, position of the mouse. Okay, you see, it didn't like it at all, and that's why it's not solving anything here. So actually, it's not solving it because it didn't like it. Let me delete this, but you get the idea, okay? Try to have a mesh with all the elements which are more or less the same size, equilateral triangles. All right. Now you have your mesh. And in here, I'm at this point where I'm telling the software, wait for me, plot the mesh, but just wait. The mesh is called omega in this case, and omega is our integration domain. The next thing I do is to assign finite elements to that mesh. And here, we're going to have 2 types of finite elements. For the displacements, remember that our unknown is displacement. Each element is going to have a linear function of displacement at the integration points, which are going to be the points in the mesh between the triangles. So the corners of each triangle, that's going to be an integration point. And between point and point, there's going to be a linear variation of displacement. That's what that means, this P1. And P0 means that for each triangle, as you can see over here, in this, just there is one value of stress. But in each triangle, there are 3 values of displacement. At each corner, there is one displacement, but for the entire triangle, there is just one value of stress. And in addition to that, I define these finite spaces. You don't have to define them again, but I'm just telling you what's going on over here. We're going to have displacement in direction 1, displacement in direction 2. U are the real displacement, V are the virtual displacements. And then we have the stresses, sigma xx, sigma yy, and sigma xy. So far, we're just defining variables. The next thing is not a requirement, but it's done here anyways to make some of the computations later a little bit shorter, is to define 2 vectors. One is the vector of stress, and the other one is a vector of strain. The vector of strain, the one notice, is exactly dx is to be the derivative in direction x. So the strain epsilon xx is this one is this first element, derivative in x of displacement in direction 1 or direction x, which is the same. Second element is a shear strain, derivative in direction y of displacement in direction x plus derivative in direction x of displacement in direction y divided by 2. The same with the other one, and the same with the linear strain in direction y. Just the definition of a strain based on displacement. And for stress, what we have is what, let's see how I do this. Okay, let me switch back to my where is that? I lost it. Okay. It's just this. So sigma 11 is lambda plus 2 times the shear modulus epsilon 11 plus lambda times epsilon 22. Let's check that. Remember, okay? Lambda plus 2 times mu epsilon 11 plus lambda epsilon 22. Lambda plus 2 times shear modulus epsilon 11. How do you see that this is epsilon 11? Because it is the first element of the vector of the strains. That's epsilon 11. This index 0, it means the first element. Plus lambda epsilon 22. This is epsilon 22 because it's the fourth element of the vector of strains. Now this is just 2 times shear modulus times the shear strain, the same for the other one, and a similar thing for the stress in direction yy. It's just the modulus times the strains. For example, if you wanted to expand this code for anisotropy, this is where you have to modify the equation in order to add the coefficients that will correspond to anisotropy. Okay. So we have the vector of stress, we have the vector of strain. The last thing to do is to define the problem, and this is actually the differential equation. So now, let me come back to here. Okay, the next thing is just this equation. Strain times stresses, and this is going to be equal to virtual displacement times stress times the vector perpendicular to the surface plus the body forces. Okay? So basically, left-hand side, stress times strain, and the right-hand side, boundary conditions and body forces. We're going to ignore the body forces. So for now, we'll just have strain times stress on the left-hand side and boundary conditions on the right-hand side. So let's see how this looks in the code. In the code, this is going to be left-hand side is the integral in the entire domain of stress. Sorry? I cannot do it because it automatically, you see, I zoom in. Okay, that's a little bit better. Okay, that's good. But before it was reducing the size when I was doing that. Okay, so the integral then is going to be, the question is going to be the integral of stress times strain. This symbol over here means transpose, but it's just stress times strain. Remember, the strain is based on the virtual displacement on the left-hand side, and that's everything for the integral on the left-hand side. this is what it gets on the right-hand side, something you're going to have to modify, which is the boundary conditions. Okay, on the boundary conditions, something that we didn't see in the integral is that we're going to have two types of boundary conditions. A boundary condition which is called a Dirichlet boundary condition, another one which is called a Neumann boundary condition. In a Dirichlet boundary condition, you tell the equation what is the solution of the unknown at that boundary. So remember that our unknowns in this case are displacements. So for a Dirichlet boundary condition, you tell the equation what is the value of a particular of that unknown at that boundary. So for example, in this case, I'm telling on the left boundary, the displacement in direction 1 is going to be equal to 0. So this one is not going to move in this direction. The next line is on the bottom boundary, the displacement in direction 2 is going to be equal to 0. With that, I'm making sure that this solid is not going to move in all directions, because if it moves, this is not going to converge. We want it to be in equilibrium. So this is not going to move in direction 1. It's not going to move in direction 2, because I told that in the solution directly over there. It means that, for example, the left boundary, the left boundary is this. This is the left boundary. I'm telling in all this left boundary, there is no displacement in direction 2. Yes, which is equivalent to, in this drawing, to adding here a condition in which you have elements that do not let that boundary move in direction 1, but they can move in direction 2. So imagine that as rollers on the left, but it does not let this move in direction 1. And we also say that for the bottom, the direction 2 is constrained, so it's the same thing. We are not letting that boundary move down. All right? Those are the first two lines. Remember, Dirichlet boundary condition, you set the value of the variable at the boundary. The next one is a Neumann boundary condition. And in a Neumann boundary condition, what we're going to set now is the solution at the boundary, but not in terms of displacement, but in terms of the stress. In every problem of just mechanics, you can either tell what is the displacement or what is the stress. But you cannot set displacement and stress simultaneously, because you either tell one or the other. It's like in the problems of flow. In problems of flow, sometimes you tell the solution what is the value of pressure or what is the value of velocity or flow rate. But you cannot tell both. You cannot set both. You choose either displacement or stress. And in this case, now we have stress. So line 74 is saying to make an integral on the right boundary of value Sx, which is just a numerical value, times the displacement in direction 1. So notice that displacement in direction 1 is the vector perpendicular to this boundary. So stress times displacement, which is a virtual displacement, is V1. That is what is going to set the boundary condition. And in this case, we're just going to set a stress. So that line is applying a constant stress Sx in this direction, and the next line is applying a constant stress Sy in that other direction. And notice that also that's multiplied times the virtual displacement in direction 2. So it's perpendicular to that line. And the last one, yes?
So just to clarify, we're keeping the displacement constant on two boundaries, and then the stress is constant on
Yes,
boundaries.
yes,
Okay.
yes. And the last one, it's also a Neumann boundary condition, but now this one is a pressure. So here you have a value, which is pressure of the well, and in order to get the vector normal to the surface, what we're using this, this is part of the code, and it means the normal value in direction x times the virtual displacement in direction x or 1 plus the normal value or the cosine in direction y times the vector in direction v2, and if you multiply that times a value of pressure, in this case this one is going to be the pressure of the wellbore, and that's called P well. So for a curved surface, then you have to use this, okay? For the other surface that were just either horizontal or vertical, you can use directly that value, but for that curved surface, you're going to need that. Right, and then that's the end of the problem, or defining the problem. After that, you just tell the software to solve the problem, and notice that the problem was called elasticity. So if you call elasticity, it's going to solve it. And the next thing is, just for convenience here, call it sigma xx, sigma yy, sigma xy. And the next step is just to plot the results. So first, I'm going to plot the deformed surface, and then the stress in direction y. So this online version is not going to do all of that, so let me do it from here. So this is the mesh, undeformed mesh. I press enter. This is the deformed mesh. That probably you cannot see much, but I'm going to change one number to make it more obvious, but I'm going to press enter now again. These are the displacements. Oh, let me see. Okay, I don't remember how to come back.
I haven't been able to figure out how to go back. All it does is make you start it all over again.
Yeah, no, but it was something like shift enter or alt control enter, something like that. Okay, but this is the solution. Now I'm plotting the values of, probably you cannot read from here, but here it says sigma xx. These are the value of sigma xx in the entire domain. By applying, let's see what I had over here. Okay, that's at the top. Okay, I have 20 MPa in horizontal direction, 10 MPa on vertical direction, and a pressure in the wellbore equal to 1. And the result is, let me zoom in. If I have more stress in direction x, then I should have concentration of stress in here, in the top and bottom. If you see the values over there, they are all negative because in this convention and for this software, we're going to use compression as negative. So the more negative it is, the more compression you have, and that's going to be the top and bottom locations because we're pressing in this direction, and here we're going to have less compression, which is here those values with a lower number. Let me change the values to make it a little bit differently. Are you able to run the software? No? Okay, let's do some troubleshooting before we continue with this, with the software. You're able to run the software? Thomas, did you try? Okay, just press enter. No, here. Enter. There, enter. Enter. It's good, it's working. It's working, okay? Yeah.
And then I'll have to go to, so it was text or it's .edp? Yeah, it's .edp, but I don't know why there's this like
Then I'll pick
copy at
this
the
one, the
end.
FreeFEM.
But when I say choose,
And then
that's all I
it
get.
pops up and then it just goes.
Yeah.
Okay, let me see.
I'm running it no problem at the moment.
Okay, so, okay, it's good?
Yeah.
Okay. Probably talk to David to see if you can help him solve the problem. What about you, Stephanie?
Okay, so I've got a million windows open, but I have it open here, and then I navigate. So when I downloaded it, it downloaded it as
No, change it.
And
Change the name. So rename and delete that txt. Okay. All right. Try again.
So it just I keep getting these windows.
It doesn't do anything.
Mm-mm.
But so where are you right now?
Okay, so let's see. What did I do? This is how I downloaded it. There was this. I had like a.
So you installed it already?
I installed it, and then it gave me.
And you run it? You open it? Or
Yeah, well, every time I try to open it, if I just double click.
it doesn't do anything?
Well, I guess before it's opened up like a bunch of. It's opened up like. It asked me to navigate to this file.
Okay, but
So let's try that again now that
okay.
I've changed the file name, I guess.
Okay, but now I think it's open somewhere. That's the issue. So you're gonna have to here. I think it's here.
Is this it?
So you have to close it.
Well, this is different.
But just close all. I think it's open somewhere. So that's why. Try to open it again now. I think now it's good.
FF file. Yeah. Okay. All right. Maybe
Okay.
I'll just close a bunch of things.
Yeah. I would do that. Just let me know if that works for you. How about you guys? Did you get it? You good? How about you, Rodrigo?
I'm stuck here. It doesn't go.
No, it's okay. Just press enter.
No, it doesn't go anymore.
Okay, just close it, escape, or just close it entirely. Okay, can you run it again? All right, so enter.
I don't know why. My file seems complete.
Can you check online with the same code? Just copy that code and try online to see if it runs. I don't know why it's getting stuck there. What about you guys?
How do you open it?
Okay, so go to the file, go to location. Okay, and then Did you install the software already?
Yeah.
Okay, do right click. Do open with. Okay, search now for FreeFEM. Go to F. All right, it's the first one. All right.
Do I have to tap something on bash
No,
to open? No.
no, it didn't do anything.
No. That should close it.
Wait. Okay, okay, terminate. Can you try again? Probably you had something open and that's why it didn't work.
I will try with Windows again.
Try with the, I don't know if it should be fine, that file, but try online.
Try online.
Yeah, with that solver online.
Like how? Where?
Try it online. Go here, try it online.
Oh. Okay.
Just delete that code and paste the code that you have.
Okay.
Were you able to run it?
Yeah, it
Works
works.
well? Okay. Good.
So for
Yeah.
how can I see the plot? Just use the swing.
All right. So you can either see it like this, or if you go to the end of the file, my file, I don't know if it is in there or not.
Is file
Go,
or
go,
you
go.
the-
Yeah, no, yeah, the file, the EDP.
Yeah.
Okay.
Just this is the plot.
Okay. Do you know ParaView? ParaView, the software ParaView. You can also export this to a ParaView format. I'll show you how to do that. Okay? You good? You? What about UBT?
Actually, it doesn't work. I made the file and then I opened it.
I think there are some issues with
Mac.
Mac.
With this one I open, just keep running and I cannot see anything.
No, but it's not running right now, right?
No.
Does you have to open?
Yeah.
No. So okay, try the photo. Go.
This one and then
Go to the file.
this one.
No, go to the file
This one.
and go right click, open with,
Other.
and then FreeFEM. Choose FreeFEM.
Okay.
Okay.
Here.
Okay. Wait.
Yeah.
Okay. Yeah, I don't know. It's getting stuck there. I think it's a problem with the Mac. I'm not sure what's going on. We'll see if we can solve it. What about you guys? You have running camera?
I guess is that. I thought it.
Yeah, and then presenter. It's not doing anything.
Let's see. I try this again.
All right, now, okay, just don't do anything, just press enter.
Yeah. So then.
Yeah, that's it.
Okay.
That's it.
Here work.
It worked?
Yeah.
Everything okay?
Yeah.
Okay, good.
Here the maximum stress was this equation.
It was X. Yes,
Okay.
yes. So, did you get to work, Stephanie? No?
Yeah, I closed everything and reopened it. And every time I try to do this, okay, great, go to that, choose, and nothing. This opens up like temporarily.
Yeah, that's the same thing that's happening with the other guys.
Yeah, so.
I'm not sure what's going on.
But there is okay, so
Although we can't
maybe we
figure out
can work
where
through their
You can hook it up to your terminal by
installation.
copying it to the dollar sign
And so I'm not
shell
sure
environment.
if I double
Okay, probably you have to do this too.
So copy this in like any terminal.
Yeah, but open a
paste.
new one, yeah.
Oh, okay.
Let's see if that solves the problem. Probably there is some library missing. So just copy
paste
that.
And then enter
Yeah.
password.
You have to put the password, your password for the system. All right, so all right, I'll give you a few more minutes, and the next thing will be to export the data. So you can plot it, and you can compare it with the analytical solution. What about now?
So copy that,
Yeah.
enter password.
Yeah.
But it actually won't let me enter anything.
No, it's entering. It's just you can't see it. Just type your password, but you won't be able to see it. But you're going to have to do it again now.
Okay.
Oh, that's cool, so it's protected, you can type it.
Yeah, yeah.
Command not found. All right, let's try that again. Enter. Now enter.
Yeah, enter your password. It's
Yeah.
installing stuff. Command not found. Let's see, what's sudo apt get installed?
folder full of the stuff that came downloaded and try to run one of the trials. None of those run.
So
Yeah, that's weird. So I wonder how you got it to
I was
to
gonna
work.
text my boyfriend and ask what he did to download it, because I couldn't get it to download, and I got really frustrated.
Yeah.
And then he works with software engineering. and
Oh,
so he
okay.
helped me.
So probably he did some of these, installed some other libraries.
Right, so I was gonna text him
Yeah.
and see if he did
Yeah.
anything special.
Okay.
download binary version file. Okay.
So guys, I'm going to look for a solution. Stefan is going to also look for a solution for the people with Mac. So who that has Mac can run it other than Stephanie? Jack, can you run it? There no. No, but here not. Okay. Okay, we'll see. I'll try to find what the solution is. But just for now, since we have a little bit of time left, let me tell you how this is going to finish. After you do the plotting, the code ends by exporting data. So what I'm telling here is to create a new file, which is called output, and it utilizes a for loop from I equal to 0 to 100, but here you can put 200, you can put 1,000, whatever you want. But more or less, you should put the same number of elements as the ones that you have in your grid. And what I'm defining here is two variables. So again, this is a comment. We have a line which is going to be equal to the size of the domain divided by 2, and is going to increase with the counter I. So what these equations means is that this is a line that goes from y, you see, is equal to 0. So this is going to be here. And x goes to the middle of the domain negative, to the middle of the domain positive. Or it goes from here to there, in that direction. So you see, I'm telling it to start here, and then it goes a distance equal to the distance of the domain up to there. So for those two coordinates, x and y, then I'm telling the software to export. First, x, put the comma, then y, put the comma, then sigma xx at position xy, sigma yy at position xy, and sigma xy at position xy. And the result is, let's see if I find it. It should be a file called output, this one.
Will it get put in the same folder that you see?
And it's going to be in the same folder, yes. And here you see the position -5, 0. All this column is a column of zeros, and it goes from -5, it should go to +5, 4.9. And here you have SXX, SYY, and SXY. And you plot this, you can open it with Excel.
Oh, can you say that one more time? Which column? S6?
Yes, it's in the code.
Okay.
It's in the code. It's XY, SXX, SYY, and SXY. But this is because I just defined it in here. You can export whatever you want. You can change this. That's part of the code. So let's do this very quickly. Here you could copy the data. Oh, that's another thing. Let me open here. I just pasted the data, and then we'll go text to columns, delimited by a comma, finish, and I can plot. Now stresses as a function of position.
How did you separate it out again by the columns?
Yes, just give me one sec.
Oh, no.
Okay, I want to plot. That's SXX, and let me plot. This is SYY. And what I did was, let me see if I have this still there. Yes. No. It already separated. You go here. Once you have your data all selected, you go text to columns. And well, okay, let me do it again. Okay. Copy the data. Paste it. But it's already taking it delimited. Let me add a new file. Oh, it's already taking it. Where go now? All right, there you go. So you have all the data, and then you go data, text to columns. This text, I told the software to separate it by a comma.
I see. Okay.
And now I'm going to go delimited. I'm going to choose here comma. And now it's going to use the comma as a separator. You click finish, and then now you have your data separated in columns. All right. So those of you more advanced in already numerical simulation, something you could do is you could export this file as a VTK file. A VTK file is a typical, or not a typical, but standard type of exporting vectors and data in 3 dimensions. What you have to do is just Google IO-VTK or VTK, and what you're going to have to input in your software, it's this load IO-VTK, and then later you have to do save VTK, and you need to tell what to save. For example, in here, I'm saving for this domain, I'm exporting a vector of displacement, I'm exporting stresses, and with under those names. And what you do after that is you read that file with a software called PayReview, which is a free software which is used a lot in order to show data for numerical simulations in 2 dimensions or in 3 dimensions. Very powerful. So if you need help with the VTK, if you're interested with that, just let me know, and I'll help you with that. But for this assignment, you don't have to do it. You just have to export this data and then compare it to the numerical solution. Okay, what about the numerical solution? The numerical solution, you also have it here. This is what is called the Kirsch solution of stresses as a function of the radius r and the angle theta. All right, so what we just did was to solve a problem in Cartesian coordinates. So, okay, no, it's not the one I wanted. Okay. So for the FreeFEM solution, or the finite element solution, you define a grid, and I think for this particular problem, the center was here, x, y, and we create all these triangles with a given position in x, y, and we solve for stresses at all those positions, but this is still a Cartesian coordinate because it's referred to a Cartesian coordinate system with x and y in perpendicular directions. If you want to solve this problem of a cavity analytically, it's much better to use cylindrical coordinates rather than Cartesian coordinates. So for the Kirsch solution, what we do is we utilize an alternative coordinate system where any point in that system is going to be given by a radius r and an angle theta, where theta is going to be measured from the stress of the maximum direction. And in this case, the maximum direction is S1. Let me double check that, but yeah, that should be the case. Yes. So S1 is in direction x and S2 is in direction y. Theta is measured clockwise, counterclockwise from the direction of S1. So for any position in here, you will be able to calculate the stress in the direction R, which is a radial stress, perpendicular to that. Oh, these arrows look very ugly. You're going to have sigma theta theta, which is called a tangential stress, or also it's called a hoop stress. And there is one thing missing, which is what? The sigma r theta. I'm not going to write it here because it's going to be a mess, okay? But here also we're going to have a shear stress, which is sigma r theta. Okay, but these are not Cartesian stresses. These are cylindrical stresses. If you want to convert that to Cartesian stresses, you have to change the coordinate system. Okay? You have to use that transformation matrix that we saw before. But I'm not going to ask you to do that, okay? But what I'm going to ask you to do is to compare stresses, say, at this line. In this line, for some triangular element, you can export sigma yy, should be actually sigma xx, and when you do theta equal to 0, the sigma theta theta will be sigma xx, and sigma theta theta will be sigma yy, and sigma rr will be sigma xx. Right? I'm getting confused with this sigma xx. I put it too close to the sigma yy. Okay. Or when theta is equal to 90, now sigma theta theta will be sigma xx, and sigma rr will be sigma yy. But it depends on what is the angle that you chose. But you can compare it very easily at either this direction or that direction. If you're going to compare it at some other angle, you have to do some transformation, which I'm not asking you to do this here. That's it. That's it for the wellbore problem. You get to run FreeFEM. Hopefully, we'll find a solution for that for those that are using Mac. And then the next thing that you can do is problem number 2. And problem number 2 consists on finding a solution for a fracture. Okay, let me tell you one thing before we move on. I gave you a copy of the problem last week, but I changed it. I changed the last part because I remembered that the fracture problem, it was a lot easier to define it as a half domain than as a full domain. So check this file online, okay? Especially for the second problem. It's just the second problem, the one that changed. Instead of simulating a full domain, I want you to simulate a half domain. Let me tell you what I mean with this. In the paper copy, before I was asking to simulate the fracture by creating an elliptical cavity instead of a circular cavity for a wellbore, and then add a pressure inside the cavity. But that created some problems because the closer you get to the tips of the fracture, you may get some errors of convergence and the mesh may not be enough. So with the new version, with the online version, I'm asking you to simulate just half of the domain in which the fracture is just going to be a line when you start. You're going to add a pressure on that line, which is going to be the pressure in the fracture, and you're going to fix displacement in direction x in this boundary, and also on the other boundaries. On the, well, in this case, on the right boundary, and on the bottom and top boundary, you tell it not to move up or down.
Can you explain conceptually how can I have stress on the
Yes,
boundary?
I can do that. So this is going to be the initial domain, okay? It's just adding pressure on this boundary. So what this is going to do is that when you add the pressure, this is going to deform. And when it deforms, this is going to create a stress around this region. So when you add the pressure, actually now you have a displacement, and that displacement is the aperture of the fracture divided by 2. So this thing is equivalent to that. And we are taking advantage of symmetry around the long axis of the fracture. Make sense, Jack?
Yeah, it makes sense, but like how do we treat this material as isotropic because we have stress and strain?
Everything isotropic, yes. So the same equations that you used for the problem before, you're going to use it for the problem of a fracture, but your domain is going to be different, and your boundary conditions are going to be different. Let me show how that looks. Okay, so this is the problem of the wellbore, and let me see what was the name. The guys using Mac may try also running this way from the command line, but I'm not sure that's going to solve the problem. Very likely it will not. You may just want to try. So this is okay. So this is that's that problem. And again, this is the domain, actually with closer dimensions to what you have to do. The fracture is there in the middle. These are the boundaries. I'm going to press enter. That's the mesh. Make sure that your mesh, you don't want a lot of meshing in the far away boundary, but you want a very fine mesh close to your fracture, okay? Also, you want a fine mesh at the tips of the fractures. Otherwise, you may get some errors in the solution. But it has to be fine, very fine in the side of the fracture. And this is the stress that you get by applying a pressure. In this case, this is, actually this is displacement. Displacement number 1, this is stress. Stress in direction x. For this case, I added, if I remember correctly, a pressure of 1 megapascal. So if you look at the values over there, it's close to 1. That's what you see over here. SXX in this direction has to be 1, has to be equal to the pressure. And also, it gets into a blue color, positive at the tips, which makes sense too, because the tip should be in tension. And this is SYY, this is SXY, shear stress. This is the SZC, perpendicular stress, and this is the deformed configuration. So with the deformed configuration, also you should be able to get the displacements at the fracture. And I want you to compare also, and now you can take a look at the paper solution I gave you. Over there, you have the equations for, not this one, but here you have the equations for displacements inside the fracture and for stresses outside the fracture. I like that you compare also those stresses and displacements with the solution out of FreeFEM. Okay? And that's everything you have to do for this project. Yes, Bethany.
So is the code for setting up problem 2, should we just put that together with what we did previously? Or
Yes.
is that still in the PDF?
It's, I think Igor put just a little bit of it, but not everything.
Okay.
Let's check.
Okay, so there's a little bit about stresses and fracture.
Yes. And he's creating the fracture as an ellipse.
Oh.
So, but don't do that. Just make it all as linear segments. And on the linear segment of the fracture, you apply a pressure with the boundary condition equal to the one of the well. So instead of P well, just call it P frac, multiply times that, and that's going to be the pressure in the fracture. So just one more thing that you, no, I like to spend a little bit more time on that. So probably we'll discuss that on Wednesday. One more thing I'm asking you in this project is to tell me where there is going to be shear failure and where tensile failure. But we need a little bit more time to do that. For now, just compute the stresses, and that's going to be it. Okay? All right, guys. Thank you.
Thank you.
I'll see you on Wednesday.